Today we're going to talk about ions. Now, in the last section we talked about atoms and elements, and we mentioned that an atom will have a neutral charge if it has an equal number of protons and electrons. But it's not always the case that we have a neutral atom, and that's where ions come in. So what is an ion? Basically, it's just an atom with a charge. Now, what does that mean? Well, it means that it has an unequal number of protons and electrons. Now, remember that there's no way for you to change the number of protons in an atom in a normal chemical reaction, but we can change the number of electrons, and so that's how we form ions. Now, there are basically two types of ions. We have cations, and cations are ions with a positive charge. We also have anions, which are ions with a negative charge. Now, this seems really silly, but this is how I've always remembered these ever since the very first time I took chemistry. So see if this helps you to remember it. So whenever I think of a cation, I always think of a little cat. You can tell I'm not an art student. And positive eyes, right? So therefore this is a cation. So cations are always positive. Okay, next we have anions. So the way that my teacher taught me to remember this would be to draw a little negative sign. And it kind of looks like an ant, right? So this is an antion, or in other words, an anion. All right, and then, you want to tell me what this thing is? Okay, that's an onion. All right, so that one's not on the test. So the only two that you need to remember are cations are positive and anions are negative. Alright, so remember that cations are positive, okay, so these always have a positive charge. Metals like to form cations, and remember that the metals are on the left-hand side and in the middle of the periodic table. Now, what does it mean for something to have a positive charge? Well, it means that it has lost one or more electrons. Now, this is important, and it's also a bit counterintuitive because you might think, okay, well, if I have a positive charge, a +1 charge, that means I've added something to it. No, in actuality, remember that electrons always have a negative charge. So anytime you add an electron, you're adding a negative charge. Whenever you remove an electron, you're removing a negative charge, or in other words, gaining a positive charge. So you can see down here with sodium, sodium likes to form a +1 ion. So how does this work? Well, you take a neutral sodium atom and you remove one electron from it, and in the process you form a sodium with a +1 charge. Now, just so you know, this is kind of important, even though it might seem trivial. Some people would write this as a plus sign. That's how I'll typically write it. Some people will write it as a 1+. Some people will write it as a +1. It does not matter, okay? But anytime you just see something with just a plus sign, that means that you have a +1 charge. All right. Now, it's also important that we know how to name these things. Turns out that cations are really easy to name because they keep the name of the metal. So sodium atom, sodium ion. Calcium atom, calcium ion. All right. It's also important to note that sometimes we remove more than one electron. So if you take a neutral calcium atom, you can actually remove 2 electrons from it to form calcium with a 2+ charge. Now, if metals like to form cations with positive charges, you can probably guess that anions are formed from nonmetals, right? Anions, remember, will have a negative charge. By having a negative charge, it means that that atom has gained an electron, one or more electrons, in order to form an anion. All right, so for instance here, we have a, back up for a sec, there we go. So in this case, we actually have a fluorine atom, and it's going to gain 1 electron. When it does that, it actually forms a -1 charge. And again, just like before, we could write this as a negative symbol, which means a -1. We could actually write it as a 1-, or we could write it as a -1. It does not matter. It all means the exact same thing. So these things are all equivalent. Okay. Oxygen, turns out that oxygen likes to gain 2 electrons in order to form a 2- charge. Now, how do we name these things? Well, turns out that we keep the base name. So fluorine, we just add an IDE to the end, so fluoride ion. Okay, oxygen, oxide ion. All right, so relatively simple. So sulfur becomes sulfide, nitrogen, nitride, iodine, iodide, and so forth. All right, so now that we understand the basics of what an ion is, let's go ahead and see if we can look at a couple of ions and determine what is the number of protons and number of electrons in an ion. So the first one we'll look at would be F minus, right, or fluorine with a -1 charge, which is a fluoride ion. So first off, how do we determine the number of protons? Remember that the number of protons is the atomic number, or Z, and we can get that by looking at the periodic table here. So here's fluorine. Okay, notice that at the top of it we have a 9, which means that this has 9 protons. Simple enough, right? Now also remember that if this were a neutral fluorine atom, it would actually have 9 electrons as well. So that's kind of our starting point, is 9 electrons. But in this case we have a fluoride ion. So normally we have 9 electrons, but somewhere along the way we gained 1 more electron, giving us a grand total of 10 electrons. Now again, this may seem counterintuitive because you think, well, it has a minus sign. Shouldn't I subtract something? No, remember that electrons are negative. So by adding an electron to it, we've actually added a negative charge. So instead of being neutral with 9 electrons, now it's a -1 with 10 electrons. All right, let's try another one. Let's go ahead and take a look at cesium. Okay, so cesium is way down here, atomic number 55. Okay, so it has 55 protons. Now if this were a neutral cesium atom, it would also have 55 electrons, but it's not neutral. In fact, this has a +1 charge, which means it has lost an electron along the way. So that means this ion only has 54. All right. What about this oxide ion here? So first off, how do we figure out protons? Well, we just go ahead and we take a look at the atomic number. So here you can see that oxygen is atomic number 8. So ordinarily, well, it always has 8 protons, but ordinarily it would have 8 electrons as well. But remember that in this case we actually have a -2 charge, so it's gained 2 more electrons. So it also has 10 electrons. Now if you're one of those people that really likes having a formula, you can actually remember this formula, that charge is equal to the number of protons minus the number of electrons. So in this case, if I wanted to have a -2 charge, and I know that I have 8 protons, the only way to make this work would be to have 10 electrons, right? You can call this x right here, solve for x, and you'd find that it has to be 10, right? Because 8 minus 10 is a -2. If if you like to do it that way, that's totally fine. I just kind of look at it and eyeball it and figure it out from there, and it seems to work for me. So let's try one more. All right, so calcium has a 2+ charge. So here's calcium. It's atomic number 20, which means 20 protons. So ordinarily it has 20 electrons as well. Oh, but it has lost 2 electrons, giving it that +2 charge. So it actually only has 18 electrons. All right. Now also, how do we name these again? Well, remember fluorine is fluoride because it's a negative charge. Cesium is just a cesium ion. Oxygen becomes oxide, and calcium stays as a calcium ion. The name doesn't change. Now, anytime we talk about electrons and protons, we need to specifically talk about what are known as valence electrons. Valence electrons are the highest energy electrons in an atom. All right, these are the electrons that are furthest from the nucleus. Okay, they're the easiest to remove. They're the ones that interact with with other atoms. Now, why do these matter? Well, it all comes back to our onions, right? Okay, so an atom's kind of like an onion. It has all these layers, and it turns out that the outermost layer is known as the valence layer, right, or the valence shell. So if I bring 2 onions together and they collide with each other, these are going to only interact on the outermost layer, right, of each onion. Okay, so that would be the valence layer, or the valence shell. So it turns out that the valence electrons are the ones that participate in chemical reactions, the ones that get shifted from place to place. They're the ones that matter the most. Now, how do you know how many electrons or valence electrons something has? Well, it turns out that if you are working with the main group elements, remember that these are the elements that stick out at the top of the periodic table. These are the ones that will say, 1A, 2A, and so forth. In fact, let me back up for a second. You can actually see here that we have our main group elements. So 1A, 2A, and then 3 through 8A. So that Roman numeral there actually tells you how many valence electrons something has. So if I'm talking about something like calcium, notice that it's atomic number 20, so it has a total of 20 electrons. So 20 total electrons. But most of those electrons aren't on the outermost shell, right? In fact, if you look at the top of the column, you'll see that this is in column 2A. So it only has 2 valence electrons. Okay, you might look at something like xenon over here. Okay, xenon is atomic number 54, so it has a total of 54 electrons. But how many of those are valence electrons? Well, if you look at the top of the column, it says that this is column 8A, so it has 8 valence electrons. All right, so relatively easy to figure out how many valence electrons something has. Okay, all of the alkali metals will all have 1. Alkaline earth all have 2. Over here we have 3, 4, 5, 6, 7, and 8. Right? Okay. All right, so let's go ahead and try a pop quiz here. Let's go ahead and see if we can figure out, how many valence electrons does sodium have? So here's sodium. How many valence electrons? 1, right? Because it's in column 1A, so it only has 1 valence electron. How about potassium? Well, it's also in column 1A, so it only has 1 valence electron. How about something like phosphorus? Column 5A, so it has 5 valence electrons. Excellent. Now, remember that the noble gases are column 8A. Okay, they're over on the far right-hand side of the periodic table. Because they're in column 8A, they have 8 valence electrons. And it turns out that everybody wants to be a noble gas, right? The vast majority of elements really, really, really want to have a total of 8 valence electrons. Okay, we call this the octet rule, although it's more of a suggestion. Okay. So what this means is that nonmetals will typically gain electrons, becoming anions, but they'll gain enough electrons that they can become like the nearest noble gas. Metals, on the other hand, will actually lose electrons in order to become like a noble gas. So let's take a look at what this means, see if we can figure out what kind of ions these different elements will like to form. All right, so remember that they want to become like the noble gases over here in column 8A. So let's take a look at something like fluorine. Okay, fluorine has 7 valence electrons, right? So what it will do is it will gain 1 electron in order to become like the noble gases. So it can have 8 valence electrons. By gaining 1 electron, it ends up having a -1 charge. So all of these guys in column 7A, the halogens, all like to form a -1 charge when they form an anion. Okay, what about column 6A? Well, all of these have 6 valence electrons. They want 8, so what are they going to do? Gain 2 electrons, giving them a -2 charge. What about column 5A? So all of these in column 5A have 5 valence electrons, right? They really want 8, which means that they will typically form a -3 charge by gaining 3 more electrons. Okay, now let's actually skip way over to the left-hand side and look at column 1A over here. All right, so when it comes to these guys in column 1A, they have 1 valence electron, right? Now, they have a choice. They can either gain 7 more electrons in order to become like the noble gases in column 8A. But gaining 7 electrons, that's not easy to do. So instead what they could do is they could actually get rid of that 1 valence electron that they have. By doing that, It's like peeling away the layer of the onion on the outside, and suddenly you have this nice filled energy level that's filled with electrons underneath, okay? So they have a choice. All of the ones in column 1A can either gain 7 more electrons or lose 1 electron. What's easier to do? Well, obviously it's easier to lose 1 electron, which is what they do. By losing 1 electron, they will typically form a +1 charge. What about column 2A? So all of the elements in column 2A have 2 valence electrons. They can either lose 2 or gain 6. What are they going to do? Well, they're going to go ahead and lose 2 electrons, right? Because it's easier. They like to form a +2 charge. Now, we're not going to worry about the transition metals right now because they're a little bit bizarre. We'll talk about those in a little bit. What about column 3A? Okay, column 3A, they all have 3 valence electrons, right? So either gain 5 or lose 3. Lose 3 is probably easier, right? So they're going to go ahead and lose 3 and form a +3 charge. Now you'll also notice that we have one thing left. We have the column 4A, and they have a choice. They can either gain 4 or lose 4. Neither one's particularly easy to do, so it turns out that in column 4A, they don't typically form ions at all, okay? So there are some cases in which they do, but the vast majority of the time they like to share electrons rather than try to transfer them. So this is very important for you to remember, okay? Column 1A, +1, then +2, then +3. We skip column 4A, then we go -3, -2, -1. And the noble gases, remember, they already have 8, so there's no reason for them to gain or lose electrons. They're already perfectly happy just the way they are. So now that we've learned all about ions, gone into some great and gory detail about it, let's actually have a little bit of fun with a tiny plunger. All right, so turns out that plungers are extremely handy, right? I carry this one with me, everywhere I go, just in case. You never know. But it's also extremely handy because it can actually remove as many cards as you want. So let's say you want 7 cards. You can pick up exactly 7 cards. And if I had an assistant with me, you could literally name any number you want, and it would give you exactly 7 cards. Now, this is a lot like atoms, right? So different atoms will either gain or lose various electrons, right? So, we mentioned that aluminum will always lose 3 electrons to form a +3, just like this deck of cards lost 7 cards due to the efforts of the tiny plunger. Now, the other cool thing about this tiny plunger is it can do more than this, right? You can literally choose any card you want, okay? And in this case, a 4 of clubs. And you can go ahead and mix that into the deck, okay, wherever you would like to. Shuffle it up a bit, and then use the tiny plunger to exactly pick up your 4 of clubs. And sure enough, it'll always go straight to your 4 of clubs, just like these ions will always form specific things, not like the transition metals that are a little bit ski-wampus where they can lose 1 or 2 or 3 and form multiple charges. All right, so thanks for sticking with me for ions.